Hello, Year 13s. I'm gonna hopefully I'll have spoken to you. I think before you watch this video, just to let you know if you haven't or you didn't turn up to that Google Meet, that I will be doing a mixture of live discussions, which will usually be brief, and recorded lessons. And mostly I'll be setting you work to do and checking that you've done the work. So I'm going to do a recorded lesson now on entropy. I really like teaching entropy. It's one of my favourite lessons to teach. I like teaching it in class. There's lots of activities and things we can do in class to help us understand. Unfortunately, I can't do that, so I'm going to do my best with the slides that I normally use. I'll do my best to explain things as best I can over a video recording. There's loads of really good stuff out there online with things like Richard Thornley and MSJ Chem, and of course your book. So don't forget, to supplement what I tell you today using other resources. Entropy, I think, is a really a kind of a tricky concept to get your head around, but in the end, the questions you get on entropy are usually quite easy, and the qualitative questions are quite easy, and also the quantitative questions as well are quite easy. And we'll move on to those more next time. We've actually got plenty of time to get through materials. There's no rush, and I'm not going to try and cover loads and loads and loads today. We'll see how we go. Okay, so entropy, you might be told, and I'll encourage you to use when writing exam questions sooner or later, that entropy is all about something called disorder. But that's not really true. Okay, what entropy really is, and I really want to explain what entropy really is. First of all, entropy is about probability, it's about chance, it's about likelihood of something happening. And we simplify it in exams and simplify it when teaching, usually, to this idea of disorder, which we'll come back to. Okay, so I'm going to use a couple of examples to try to explain what diffusion is. Sorry, beg your pardon. What entropy is, in order that you can understand it before tackling the kind of questions you're going to get in the long run. I'm going to start off using an example I found in a textbook really quite a few years ago. It was an old Nuffield textbook, which I quite liked for certain topics, and it explained, I thought, entropy really quite well. Okay, so we're going to talk about diffusion. You're told in biology right from year 7 what diffusion is, this idea of movement of particles from a region of high concentration to a low concentration. But nobody in biology will tell you why that happens, that it just does. Marvellous. But you know that if I took a vessel like this one here, this is one big long tube with a divider down the middle, and I put in that tube, I put the divider in. On the left hand side of the tube, I put some hydrogen sulfide, and over on the right hand side here, as we look at it, it's empty. Well, it's got air in it. It's not a vacuum. It's got air in it, so the pressure's equal. But I've got, on this side, I've got hydrogen sulfide. On that side, I've got air. If I remove that divider, you all know quite intuitively, right back from year 7, that both jars will have a 50-50 mix approximately of air and hydrogen sulfide in a very short space of time. But no one will ever have explained to you before, I don't think, why that happens, except they'll just say, diffusion, marvellous, something like that. I'm sorry, it's early. Right, okay, so I'm going to try and explain it bit by bit for you as best I can. I'm just going to pause a moment to give myself a chance to think again. Here's that tube. It wasn't on its side before. It wasn't its side. So here's the tube again. The divider's still in place, and instead of having this completely full of hydrogen sulfide now, I've just simply got 6 molecules of hydrogen sulfide in there, and on the right hand side I've got air over there again. Okay, and the whole thing's an atmosphere of air, but I've got 6 molecules of hydrogen sulfide on the left, and there's a divider blocking them from getting over to the right hand side. Now, each one of those molecules of hydrogen sulfide, we're going to we're going to give a notation to, or we're going to annotate with either it's on the left or the right. If it's on the left, it's going to be L. This one is on the left, so it's L, 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 L. So we've got representation at the moment of 6 L's because all the molecules of hydrogen sulfide are on the left-hand side. Easy peasy so far. If I remove the divider, it might be that one of those molecules of hydrogen sulfide shifts across to the right-hand side, and we've now got a representation of L, 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 R. Okay? And there's a number of possible combinations of where those molecules could be now, either on the left-hand side or the right-hand side. Okay, so that's the picture I just showed you. Many, many possible arrangements of those 6 molecules. Each can be L or R. There are 2 arrangements for each molecule, right or left, L or R. And we can calculate very easily the number of possible arrangements that there are in total. And you end up with 2 to the power of 6. Okay, so 2 possibilities, 6 molecules, 2 to the power of 6, which is 64 possibilities. Okay, only one of those possible arrangements is L, 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 L. All of the others have a mixture of right and left, except of course the one where all the molecules are on the right hand side. All of these things are possible arrangements of those. Okay, so in other words, if you were just to allow those molecules to move around randomly in that glass jar for a period of time, however long that might be, and there is a 1 in 64 chance that all of the molecules are going to be on the left hand side at any one time, if you just take a photo snap at any one time. Likewise, there's a 1 in 64 chance that there'll be all the molecules on the right hand side, and it's overwhelmingly more likely, so 62 out of 64 or 31 32ths, that there's going to be a mixture of molecules, some of which are on the left, some of which are on the right. In reality, of course, there aren't 6 molecules. There's many more molecules, and so the chance of all the molecules all being on the left are very, very small, and the more molecules there are, the smaller that possibility. And so, in other words, diffusion happens simply because it's more likely, from a probabilistic point of view, that the molecules are going to be spread out. It's just not very likely you're going to get this 1 in 64 chance of them all being on the left, or 1 in a gazillion chance if it's more molecules. Right, and so in other words, chance is operating in diffusion, and chance is also operating in chemistry. And the trend, we say, is from order to disorder. Order would be when all the molecules would be tucked up on the left-hand side, L, 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 and disorder, this more random arrangement with some of them left, some of them on the right. Okay, there's loads of examples of this. If you go online and look up examples of where entropy is happening, you'll get loads of classic examples. The one that they used to do with me at school was the bedroom example, and I quite like this one, so we'll do this one. Here's an example of what my bedroom looked like when I was a teenager, including all the including all the teddy bears up there. But certainly my room was a bit of a mess when I was a teenager. I didn't look after it particularly well. And here's what I wish my bedroom had been like. I like the thought of it being tidy. But which one of those two things is more likely to happen? Now, if you think about it, there's maybe only a small number of ways, maybe 10 ways for argument's sake, that your room could be considered to be really, really perfectly 100% tidy, with everything in its right place, and the bed made, and the books all in the right order, and everything really hunky-dory, lovely and tidy. But there are maybe a trillion ways of your room being messy. You could go in there, chuck all the clothes around, and it would still be messy. You'd still say from a distance, if you look at that room is messy. So there's a gazillion ways, let's say 1,000 ways of your room being messy, and maybe 10 ways of your room being tidy. And so it's overwhelmingly more likely that your room is going to be messy, assuming that you're not constantly putting work in to make it tidy. What I'd like you to do is to watch this sandcastle video. I really like this video, so I'm going to sit and watch it with you. How professional I am. Where is it? There we go. Wonderful. Brian Cox explained entropy there, I think, beautifully, and explained this idea that as you uh, increase the chance, as you increase the number of ways of something existing and looking the same to the observer, the higher the probability of that thing occurring. So in other words, the higher the disorder, the higher the entropy, and also the entropy always increases. Okay, so we're going to talk about this more and more. We're going to talk about chemistry examples and the kind of things we're going to get in exam papers and all that kind of stuff. So hopefully you've got a sense of kind of what entropy is at the moment. And some of you will be feeling, well, how do I apply this to chemistry right now? And I'm going to now start kind of that process a bit more. And we're going to talk about just working out which systems have the highest entropy. So going back to really simple kind of questions now, which systems have the highest entropy, and it will help you then to answer the kind of questions you're going to get. And let's start by talking about solids versus liquids versus gases. So solids have the lowest entropy. There is really, if you think about it, only kind of one or a very small number of ways the particles in the solids can be arranged in such a way that it would be a solid. So they've got to have this kind of perfect lattice arrangement, let's say. So they have very few ways of existing or being arranged that it is a perfect crystalline solid. So solids have a very low entropy. Liquids, the particles in the liquid are able to move around and still be the same stuff. So if you looked at a liquid and looked at it 30 seconds later, the particles might have moved around a bit within it, but you won't be able to tell it will look the same to you. And so there's many ways of the particles in the liquid being arranged where it looks the same. So you can think of that as having a much higher entropy than solids. And gases, where the particles are moving around much faster, they're further apart, they have higher entropy. Again, there's many more ways of them existing such that they look the same to the observer. All right, so that's a way of thinking about it, and I'll show you a graph of this in a second. Hang on a second, I'm just going to pause the video. At this point I normally play Celebrity Deathmatch, and you've had a little chat in your groups. There used to be a program on TV years ago. It was called Celebrity Deathmatch, and they used to have animated celebrities just beating each other up for no reason at all, and everyone used to watch it. But anyway, with this game, I get you to move to the side of the room to decide which you think has the highest entropy. And if I put this up, everyone would hopefully point to gases having higher entropy than solids, and gases would have higher entropy than liquids, and you'd either move to the side of the room or point to the correct side of the room here. Okay, and liquids would have higher entropy than the solids. Now what you need to know, this is what I just paused the video to check that I had this graph on here. Here we go. Here's a graph that you need to be comfortable with, familiar with. So if you start at very low temperature, say absolute zero of a perfect crystalline solid, that would have an entropy of 0 or very close to 0. As the temperature of that solid increases, the entropy increases. The particles are vibrating around a little bit. That means they have a bit more entropy. Take my word for it, please, if you don't find that a very comfortable idea. But as the temperature increases, you need to be comfortable with the fact that the entropy increases, okay, somewhat. And then eventually you'll get with a solid usually to a melting point, and it will turn into a liquid. The temperature during that phase transition doesn't change, of course. 0 degrees for water, for example, you go from ice to water rather, and the entropy is much higher than the solid at the same temperature, okay, for reasons I mentioned earlier on. And then again, as you increase the temperature of the liquid, the entropy increases, and then you get a big jump now as you go from a liquid at its boiling point to a gas at the same temperature. Once you've gone through that phase transition, the gas would have a higher entropy, and the hotter it is again, the higher the entropy. Okay, so you need to be comfortable with that idea. If you want to make a note, that's something you must know. Okay, so here we go. Entropy deathmatch again. Imagine yourself running to the side of the room of the box with the highest entropy, low temperature or high temperature. I've already told you the answer. The answer is, of course, that high temperature has the highest entropy. And here we go. This is from the textbook. Higher temperature substances have more entropy because each individual particle can access additional ways of vibrating and rotating. There are more arrangements which look similar to the observer. You will not have to state this in an exam. You need to know that high temperature substances have more entropy. You need to know that solids have low entropy and liquids have higher and gases have higher. You don't need to be able to quote this, okay? Hopefully it helps you to understand, though, rather than confuses you. Entropy deathmatch, solid versus solution. You're all going to run across to the side of the room, which is solution, I guess, because liquids have a higher entropy than solids. And this one usually confuses people. What do you think? I'll pause and you decide. And the answer is, of course, it depends what the temperature is, sir. And if it's at room temperature, if it's at 298 Kelvin, of course it would be CO2 because it's a gas, and water at that temperature would be a liquid. But if it's, anyway. Gas in a large box and gas in a small box. Okay, let's say you've got the same number of moles of gas, but one's in a large box, one's in a small box. What do you think? Well, the answer is gas in a large box should have higher entropy. There's more possible arrangements of those gas particles within that large box. That's not one you're going to get asked. I don't really know why I've kept it in there, but I think that's true. Ethanol versus methanol. Have a think about this one for a sec. Now, usually there's 50-50. People don't know the answer to this, and I haven't told you yet, so why should you know? But hopefully some of you will have guessed that ethanol has the highest entropy. The answer, or the reason for that, is that longer molecules have higher entropy than shorter molecules, because again they've got more ways of kind of existing which look the same to me, the observer, looking down on it. And that's because the molecule can rotate and twist and turn and wibble around and still be ethanol, whereas methanol is a much smaller molecule and there's less degrees of kind of rotation that are possible for it. So longer molecules, bigger molecules, tend to have higher entropy than smaller molecules. Okay, particularly if they're molecules which have got flexibility within them, they're not kind of constrained in some way. Multiple choice questions then. When ammonium nitrate crystals dissolve in water, the entropy of the system A, B, C or D? What do you think? Ammonium nitrate crystals, solid ammonium nitrate crystals, dissolve them in water. Does the entropy stay the same? Go down, go up or go up? Well, it goes up, of course. Why? C or D? The answer is D. The ions are arranged more randomly in the solution than they are in a crystal. Simple as that. Okay. You would talk of you could say, if you were given this as a question to answer, you could say because it's a more disordered system, liquids or solutions have higher entropy than solids. D will do. Another one. It's not multiple choice this time. You've got a few questions here you can think about and answer. Pause the video now, answer these questions and compare them with my answers in a moment. Hopefully you took a little bit of a pause there and had a chance to think about what you might say to questions like this. Again, these are all questions which are meant to kind of promote discussion about entropy in class rather than be the kind of things that you're going to be asked in exams. Okay, so there's plenty of exam questions coming your way. This is to promote the discussion in lesson 1. So those of you panicking now thinking, how am I going to answer that in an exam? You're not going to get this question in this way. But perfect crystals you would describe as having zero entropy at 0 Kelvin. At 0 Kelvin, a perfect crystal would have particles kind of fixed in one place. Okay, and it is defined really that at 0 Kelvin perfect crystals have zero entropy. There's no room for those. There's no ability for those particles to move around at all. There's no vibration at absolute zero, and there's no movement of those particles around anywhere. They're all perfectly arranged, and so they have zero entropy. Okay. As soon as you start moving any of the particles around, it's no longer a perfect crystal, and so to be a perfect crystal, 0 Kelvin must be zero entropy. Why do liquids have higher entropy than solids? Well, it goes back to something I said briefly before, that there's more ways of the particles existing, and where it looks the same to you as the observers. They can move around and it will still look like water to you if it's a liquid. And why do gases? Same answer really. Gases have much more freedom. The particles have much more freedom to move around at higher temperature as well, of course, typically. And as they're able to move around more freely all over the vessel, it looks the same to you, and without any kind of interactions between the particles, they have higher entropy than liquids and much higher than solids. And butane has a higher entropy or standard entropy than propane, and that's because under those standard conditions that when we start to look at real examples in data books and so on, when we compare butane to propane, butane's a longer molecule. There's more degrees of freedom, more rotation, wibbling around it can do, so it has higher entropy than propane. And you can find these numbers, entropy numbers, in your data books, these standard entropy. So I'd encourage you now to dig out your data book and have a look at the data book to see what's in there. These numbers, I made these slides years ago, so these have probably come from A-level data books. They might be slightly different to your numbers, but they should be very similar. Entropy is given the symbol S, and the units are joules per mole per Kelvin. You need to know that. You need to know the units for entropy, joules per mole per Kelvin. And you will notice that these are standard entropies, by the way, so entropy at standard conditions. And they would vary, of course, at different temperatures. But even at room temperature, diamond and graphite have extremely low entropies. Diamond has an entropy of 2.4 joules per mole per Kelvin. Graphite's very similar, marginally higher. You wouldn't be expected to know these numbers, but you'd be expected to be familiar that the solids are very low. As you go to liquids, they get higher. Interestingly, there's not much gap there, is there? But liquids are higher, and then as you get to gases, they jump up again. They're much higher again. Okay, so that fits with, I think, what I've taught you. You should have a little look in your data books now to see where you can find standard entropies. I'm not sure this is adding a huge amount, this next slide, but I'll mention it anyway. So entropy is essentially a direct mathematical computation of distribution of available energy. That's the kind of hardcore way of thinking about it. But essentially, what I've taught you so far is the way to think about it. The more ways of something existing, the higher entropy it is. But this is a kind of more technical definition to it for those of you who are kind of more physicsy inclined. Okay, right, I think I might stop there. I'll stop there. I'll just have a little flick ahead there. So this slide pack, I normally get to about here when I'm doing the lesson. By the time we've had a few discussions, watched a couple of other videos as well, had a chat about it, is about where I get to. So all I want you to do this time is to acknowledge that you've made a few notes on what I've said so far, supplemented with a textbook. Okay, that's all I want you to do today, nothing more than that. So it's been a half an hour video, quite a long video, apologies for that. Hopefully you've got a sense of what entropy is. Please now just make a few notes on entropy using a textbook to help you. Don't worry about any quantitative stuff at all, that's going to come. We've got plenty of time to get through this, so please don't fret. And just upload a photo of what you've done, or if you make notes electronically, you can share them via the Google Classroom. I want to know that everyone's doing what I've asked. I want to see a copy of your notes, folks. That's it. Thank you and good night.